going to be negative 1. So there's an edge between two vertices I and j, the entry is a negative 1. So between say 1 and 2, there's an edge between 1 and 2, so the entry is a negative 1. There's an edge between 1 and 4, so the entry is a negative 1. If there's no edge between two vertices, the entry is a 0. Because the adjacency matrix is also going to have 0 if there's no edge between two vertices. Right? So that's the way we develop the Laplacian matrix. So the diagonal is a degree. The other entries are either a 0 or negative 1. A 0 if they don't have an edge, like 1 and 3 don't have an edge, so the entry is a 0. If the two vertices have an edge, the entry is a negative 1. Okay? So now we feed this to the eigenvector program. So it's going to give you again the eigenvalues and the corresponding eigenvectors. We are just interested in the eigenvalues for this application. So this is a graph of 5 vertices, so we are going to get 5 eigenvalues. Now, all the eigenvalues, so there's a property of this Laplacian matrix that all the eigenvalues are going to be 0 or positive. Okay? Is that clear? So you see here there's no negative eigenvalue. Now, if you see only, again you're guaranteed to see at least 1 0 among the eigenvalues. Okay? So if you see only 1 0 among the eigenvalues and the rest of the entries are greater than 0, it means the graph is connected. So you look at this, these 5 eigenvalues, you see only 1 0 and the rest are greater than 0. So which means this graph on which we did all this analysis is a connected graph. So all the vertices are reachable from each other. Is that clear? Then the smallest positive or value greater than 0, okay, smallest non-zero positive eigenvalue, which is 1.586 here, is what is called the algebraic connectivity of this graph. Okay, so the smallest positive eigenvalue of the Laplacian matrix is called the algebraic connectivity of the graph.
0 won't count.
0 will not count. 0 is, as I said, non-zero. Okay, smallest non-zero positive eigenvalue of the Laplacian matrix. Now, you could wonder again this 1.586, how close, like how much, is the connectivity there. Look at the largest eigenvalue that you got, which is 5. So if the graph was a complete graph, okay, so if all these 5 vertices have edges between them, like 1 is connected to 2, this is to 5, and so on. Every vertex is connected by the vertex. Then the eigenvalue could go all the way to up to 5. Okay, so now you can again have a more deeper understanding of how connected the graph is. So it's 1.586 and it could go all the way up to 5. So you can even take the ratio if you want to have a feel of it. But relative basis, you can understand how connected the graph is. Is that clear? For a given graph alone, you can measure the extent of connectivity. Now, as I said before, you can do this analysis for.
Sir, can you please again little brief?
Okay, so that 1.586 is the smallest positive eigenvalue, right? So that's called algebraic connectivity. Now, if you want to go further and have more feel of, okay, what is this? How close, how much, how well the graph is connected? I know it's connected, but how well it is connected, okay? Then just find out the number of vertices, or even look at this, the largest eigenvalue is also 5. So if the graph was completely connected, it's a complete graph, then the smallest eigenvalue could also go all the way up to 5. But it didn't go all the way to 5, it was 1.586. So that gives you an idea of how well connected the graph is. If for some other graph of 5 vertices, if the algebraic connectivity came out to be 2.3, you can have a comparison of the numbers. Okay? Is that clear? Now, if you want to assess the importance of any edge in the graph, as I just set here. You could remove that edge. So if you want to assess importance of this edge or any edge, so just remove this edge, find the algebraic connectivity, and with this edge find the algebraic connectivity. You could see the difference, how much the algebraic connectivity changes. Now, in the traditional graph theory topic, you could come across something called just connectivity. Okay, there connectivity just means the number of edges you need to remove from a graph so that the graph gets disconnected. So for both these graphs here, the traditional way of looking at connectivity is just 2, because you have to remove 2 edges to disconnect this graph. Again, you have to remove 2 edges to disconnect this graph. So the traditional way of looking at connectivity does not give you any idea about what, how important a particular edge is to the graph. But by using this algebraic connectivity measure, you can find out how important a particular edge is to the connectivity of the graph.
So then the algebraic connectivity is like the lowest value, and the traditional connectivity is like.
No, traditional connectivity is just the number of edges that you need to remove from a graph to make the graph disconnected. What I'm telling is, for both this graph here, the traditional connectivity is 2, but they don't give you any idea of the importance of any particular edge to the connectivity of the graph.
Yeah.
So that's why the algebraic connectivity could be used to assess relative importance of any particular edge. So the numbers you don't compare 1.382 to 2. Don't compare like that. Okay. Just you compare 1.108 with 1.382. So that shows that the presence of this edge increases the connectivity from 1.108 to 1.382. So if you are more like trying to find the percentage increase, some people will do that. It's a good way of analyzing. So this is the difference. So it increased from 1.108 to 1.382, and you take the ratio like this. Okay? Clear? Now, one more thing. So again, you know how to find the algebraic connectivity for any graph, right? So write down the Laplacian matrix, find the eigenvalues and the smallest positive eigenvalue, 1.108 and 1.382. Now, I said if the graph is connected, there's going to be only 1 0. But if the graph is not connected, so something like this. So the top graph, it has 7 vertices, and it's not a connected graph, right? So if you run through the Laplacian matrix and find the eigenvalues, you'll get 7 eigenvalues corresponding to 7 vertices. So now you see there are 2 zeros out here. Why 2 zeros? Because the graph has 2 components. Okay? So if the whole graph was connected, we say the graph has only 1 component. So a component by definition is the largest set of vertices that are reachable from each other. Okay? So if the graph is connected like this, we say there's only 1 component. The whole graph is in 1 component. Whereas if the graph is not connected, it has multiple components. So how many components are there? You will get that many zeros among the eigenvalues. So this graph has 2 components, so it has 2 zeros. So by looking at the number of zeros among the eigenvalues, you can determine the number of components in this graph. Is that clear? Okay. So 2, 3, 1, 2, 3 are in 1 component, they are reachable to each other. 4, 5, 6, 7 are in another component. Of course, then there's no notion of algebraic connectivity, because algebraic connectivity makes sense only if the graph is connected. So if the graph is not connected, we are more interested in finding out the number of components in the graph.
So what is the useful of this?
Yeah, the connectivity. Like in the previous case, if I want to assess the importance of an edge for connectivity, I can remove the edge and find out connectivity with and without the edge. Or even for a single graph, if you want to have a feel of how connected the graph is, just find the algebraic connectivity and compare to the maximum possible value, which was 5, right? The graph is not connected, just find out the eigenvalues and count the number of zeros. That will give you the number of components. That's a good thing. Instead of running first search, you can now find the number of components.
2 components, it has 3.
Only 2 zeros.
No, it has 3. 1, 2, 3, 3 components, right? So why you said?
There are 3 components. Only said this is one component and this is another.
Ah, okay. In total.
Yeah.
In total. Yeah.
So that's an extension of the application. Now one more extension that is possible. Once you have all those eigenvalues, as I said, there's guaranteed to be at least 1 zero among the eigenvalues, right? So if the graph is connected, you know what a spanning tree is? You've seen that in any algorithms data structure class? No, not. You never come across this term called spanning tree. So spanning tree is basically a collection of edges among the edges in the graph such that there's no cycle. You know what a cycle is? You can start from a vertex, go around and come back to the starting vertex. So a tree should not have any cycle. And spanning means it spreads over all the vertices. So what I mean by spreads over all the vertices? All the vertices are part of the tree. So for the graph of 5 vertices out here, this graph, I can draw multiple spanning trees. One spanning tree could be like 1, 2, 5, 4, 3. So this is a spanning tree of these 5 vertices based on the edges of the graph. Again, it's just a subset of edges because it cannot have all the edges, right? So a tree of n vertices can have only how many edges? N minus 1 edges. Okay? A spanning tree of n vertices can have only n minus 1 edges. Okay? So, is this the only spanning tree possible for the graph? Any other spanning tree? This is also a spanning tree, right? Just all the 5 vertices are covered and they are all reachable to each from each other, right? So, clear? So this is a tree of these 5 vertices. This is another tree of 5 vertices, a spanning tree of these 5 vertices. So you could come up with several such spanning trees for the given graph. So you may be wondering how many spanning trees there are possible for a given graph. Because again, that's a measure of connectivity. Because if the given graph itself is not very connected, it has very few edges, it's barely connected. Like for example, it is something like this. If it's itself a tree, then there's only one spanning tree possible for the graph, right? So a graph is a tree, okay? Or a tree is a graph. A tree is a graph. The opposite need not be true, depends whether the graph has a cycle or not. So here this is a tree and it's also a graph. But this is a graph, but it's not a tree because it has cycles. So that's why we're interested in finding how many spanning trees are possible. So if you find the number of spanning trees for this as a graph, there's only one spanning tree, so that gives a measure of connectivity. Whereas if a graph has multiple spanning trees, possible spanning trees, then it's more connected. Is that clear? So how many spanning trees are possible for this graph? We can determine that using the eigenvalues of the Laplacian matrix. So how? Just multiply all the positive eigenvalues. So leave out the 0, just multiply all the positive eigenvalues and divide the multiplication, the product of all the eigenvalues. Okay? So take the product of all the eigenvalues and divide by the number of vertices. So in our case, 1.586, 3.4, and all these numbers are the eigenvalues, right? So